Yes, I have a number of my own students in this audience here tomorrow, and I know they're very nervous to talk in front of me. So I don't know if I should be as nervous talking in front of them. But anyway, let's see how it goes. So, yes, so I'm heading up the cybersecurity research team, but this team definitely is part and is going to merge definitely with the digital forensics team of Professor Venter. So it's not that there are two separate groups, we actually work as one group, especially, and Professor Venter already indicated very nicely that 80% of the work is in digital forensics and 20% in cybersecurity. In my case, it's just the other way around, where 80% of the work is in cybersecurity and 20% of the work in digital forensics. Okay, maybe just to make sure that we're all on the same page, what is cybersecurity? So I always like to go back to a well-formulated definition, and in the space of information security and cybersecurity, the best reference is what is done by the National Institute of Standards and Technology in the United States. So they refer, and that glossary, I've put it up there, glossary of key information security terms. It's a very, very useful resource, and I can highly recommend to usually go back to that. But they say that cybersecurity is the ability to protect and defend in cyberspace. So I think there are three very important concepts here. Classically, or should I say, traditionally, conventionally, cybersecurity, and when I did my master's degree and doctoral degree, and for all the years research following that, there were always two main components. You either prevent something by means of protecting something, or you try and defend. So if someone sidesteps a mechanism that you've implemented to protect the system, then we must have some good technology implemented that will bring that to the fore. Cyberspace on its own, if you use the definition of the National Institute of Standards and Technology, refers to a highly interconnected environment. It refers to internet, any telecommunications network, and so on. That definition, you can read it in the URL, was already formulated in 2013. And of course, I think you cannot talk about cybersecurity if you don't include what I've said at the bottom here: people, society, businesses, and so on. But there's one more important thing, and this is the crux of my presentation, is the fact that with the advancement of AI, and specifically generative artificial intelligence, we need to put discovery of threats onto the agenda and what we are trying to do. So it's not only good enough anymore to have a prevent and a defend, but we also need a discovery of threats, and that is the main focus of what we do. So if I have to say what is the grand challenge that my research group and myself are working on, it can be formulated by saying it deals with the safeguarding of platforms against cyber threats that potentially cause harm to societies, businesses, and individuals. So all of the research projects working with me either is looking at threats possibly on individuals or businesses or societies in the large. One project that two projects on the idea of societies in a large from a cybersecurity perspective is we did a lot of work in identity deception, detection, discovery, as well as where we looked at using AI on social media platforms to proactively discover pedophilia and other harmful intentions like that. But that's important for me. That is what differentiates cybersecurity from computer security or information security, is the larger impact that we're looking at. So my research is divided in 3 thrusts. This is thrust number 1. And this deals with the discovery of identity deception. So basically what to do is to leverage advanced technologies, intelligent technologies, of course AI, Gen AI, and so on, to actually detect identity deception or fake identities. Just this week or last week, there was a report released here in South Africa of the 10-fold increase on people who use fake identities. So not only here, but globally, especially for young next generation researchers, this is a fantastic area to get involved in, especially if you're interested to do a convergence between cybersecurity and artificial intelligence. So, and I should also say, I see Dr. Ndlopfu here this morning. Good morning. And we had a very successful collaboration with Nikki's, and we provided infrastructure for the ground work that we've done for this. That work has been very well published internationally, and as I said, we got some good high-performance infrastructure to do the modeling. Of particular interest is the whole thing of bots and humans, and especially with generative AI, it becomes increasingly important to know that this was generated by a bot or a machine, and this was generated by a human being. So those are all interesting areas. Thrust number 2, and here you can see the overlap with Prof. Venter's group. We focus on cybersecurity, digital forensics, and artificial intelligence. So here the aim is, if we look at a digital forensics process model, in other words, all the tasks and steps that you have to execute when you engage in a digital forensics investigation, which of those tasks can we improve by using machine learning? And so I've already mentioned one of the projects, very successful, was also done in collaboration with the CSIR, where Homakazi Ngayani developed a model to actually discover harmful behavior on social media platforms. So that's all in thrust number 2. Thrust number 3 is cybersecurity and intelligent discovery of threats. Here we want to look a little bit wider, and 3 of my students who are here this morning will talk a little bit about things like continuous authentication and the risk and privacy in VANET's vehicular ad hoc networks. So I think I'm going to leave it there. There are 3 main thrusts, and within those we're looking at various research projects. It will be not good of me not to mention my research team here this morning. So Eunice Hammond is here. She will talk a little bit later. Henry Gedudu is also here. Henry, thanks, there you are. And Mr. Christopher Njaravani. Christian Klopper is busy doing an MIT degree, in Tsika Faku, an MIT degree, and I've mentioned Homakazi Ngayani. She just graduated cum laude with an MSc and will continue with a PhD, all in the area of using AI on different platforms, especially social media and cybersecurity. Then Mr. Innocent Mbona, he will be graduating, he's submitting this week or next week for the PhD. His work specifically focused on the detection of malicious bots. Very important area right now globally as well. Daniel Jabbar is working on the intelligent discovery of insider threats. So insider threats are employees of companies. That's one of the most difficult areas to actually develop solutions for. And so we again look like what can we use from AI, using, for example, email data and so on, to detect things like threats like disgruntled employees and so on. Okay, Pamela Njoli, she's working in cloud security, and Mr. John Dack is working in testing AI and safety of systems. And I should also mention Dr. Moses Lamini's from the CSIR. He did a PhD under my supervision some time ago, but he is really delivering an excellent support for the research team. All in all, that's what I have to say. Thank you very much. Thank you. So Hein, are we automatically flowing into the following, or Renier, will you?
Okay, the first speaker is talking about ransomware detecting using PE entropy, Mr. Andrew Singh. Please note, the sessions are quite short, so we will have a question and answer session at the end of the session, not after each talk. Thank you very much.
All right, good morning everyone. Trust everyone is doing well. So my name is Avinash Singh. I'm from the Department of Computer Science from the University of Pretoria. And I would also like to thank Sanran, Nikki's, as well as Issa for giving me the opportunity to present here today. So my talk is on ransomware detection using PE entropy. So without further ado, I'll take you to the table of contents. So first of all, we'll speak about ransomware statistics. But before we can get there, let me first discuss what ransomware is. So ransomware is a growing malware that has plagued the internet and encrypted files of thousands of organizations. So the aim of ransomware is to encrypt your data and then hold the decryption keys for your data as ransom. So this is a very an effective move for threat actors because they're actually using an inbuilt security functionality that is privacy through encryption, actually encrypting your data and then making organizations unable to use their data and then disrupt business operations. So then, since this is a threat sort of attack kind of model, we need to also then be able to detect ransomware promptly. And to do this, we're using something called PE entropy, which is portable executable entropy, which I'll speak about a bit later. And the growing technology nowadays is machine learning. So we're also then going to adopt machine learning into the mix, and then I'll present my results and conclusions. Okay, starting off with some statistics. So 66% of organizations were hit in 2022. This comes from the State of Ransomware report from SOFIS 2023. And the most common ways that ransomware infects organizations and computers is either through vulnerabilities, through unpatched systems. You know, some legacy systems cannot be patched due to version conflicts and compatibility issues. And 29% due to compromised credentials. So those compromised credentials can either through social engineering attacks or default passwords on applications that have been installed and not changed. Then 76% of attacks resulted in data being encrypted. So the remainder percentage could be through detection models that organizations have employed to prevent the attacks from happening in the first place. And adversaries have stole data in surplus of 30%. So we've noticed a shift in ransomware, not only to encrypt data, but also to extort data. So it's a two-prong attack, where not only do they encrypt your data, they steal your data and demand payment, otherwise they will publish that data that they've stolen to the dark web. And 97% of organizations had their data returned back to them. And we can see organizations are still resulting into paying the ransom. As you can see, the statistics is 46%, which has remained steady. Now, security researchers often advise not to pay the ransom because it just encourages ransomware threat actors to continue doing what they do. Others have resulted into not using backups due to complexities of storage and also cost involved thereof. So the average cost that ransomware demands for large organizations is $1.54 million. Now, for a small organization, that's out of the question. They aren't going to pay that. So usually their data just gets encrypted and they're pretty much stranded. So 59% of organizations had cyber insurance. So cyber insurance is a growing thing now in industry where companies actually get insurance providers to cater for their losses. However, that has its own set of complications through compliance and so forth. And only 15% of these attacks do not have any insurance. And then the mean cost or recovery cost through the attack, it can be anywhere for a number of days, weeks, or months, is $1.8 million. So as we can see, the amount to recovery also then is similar to the ransomware demand amount. And often backups are used to actually restore it. However, some other people also then result into paying the ransomware attack because it's difficult for them to recover from attack, so they just instead result in paying it. So what is the state of the art with ransomware detection? So we first start off with static detection. This involves the ransomware without analyzing it without any execution. So this means when executable file that's specifically target the Windows operating system is landed either through the network or on your machine. Static detection is what would occur without the executable executing. So in other words, at this state, there's no harm that can become to the computer. And in doing so, we can look at the dynamic link libraries. So what sort of libraries the executable is importing can also then tell us the behavior of what that executable might do. We can also then use text and semantic searching through the executable to see if there is a ransomware message embedded within that executable. We can also then look for signatures and so forth, which is what antivirus softwares also look at. And then we can also look at the PE information, which is the portable executable information. So the PE information I'll speak about in the next slide. But moving on to the dynamic detection, we have things where we actually execute the ransomware, most likely in a sandboxed environment such that it cannot affect the host machine. And we look at the execution analysis, so things like the API calls, the registries, the functions, and so forth. We also then look at network activity on what servers these malware, ransomware specifically tries to interact with, and usually the network activity will reveal the command and control server that ransomware uses. And I like to look at dynamic detection as a kind of hiding sort of scenario where it's not very easy to actually find if something is ransomware or not. So usually in dynamic detection, it's often a throw and catch ball game. Nowadays with threat actors advancing the techniques, they like to automatically detect when things are being sandboxed, and therefore they will not execute anything maliciously. And that has often also then resulted into dynamic detection not working as effectively as it used to. So moving on, we then bring forth intelligent detection. So the typical approaches were manual observation, manual analysis through a security researcher or analyst, looking through the executable, looking through the process memories and histories and so forth, trying to detect whether or not something is malicious. So that obviously takes time, and it's not as fast as the ransomware that will be encrypting your files, all right? So I like to look at that as ever evolving and ever improving through the adoption of machine learning specifically. And I'd also then like to think of intelligent detection being a bug spray, which continuously evolves over time, where new chemicals are added to kill any sort of insects. So let's take cockroaches, for example. And cockroaches become then immune to that insecticide, so then new formulation is needed and so forth. So very similarly, intelligent detection needs to constantly evolve. So talking about portable executable, so that is basically an exe file that you find in a Windows operating system. It dictates how the operating system should open that file, what libraries it needs to load into memory, and also how to allocate the memory and the different sections thereof. And entropy is just a measure of randomness. This is often used in mathematics and information theory, where we're able to determine if something is following a specific pattern or if it's completely random. So a low entropy value dictates a specific structure. So that can be structures that are known. So very often you'll find benign or good applications actually have a very transparent structure where you can exactly see how the executable is going to be executed. And then we often get something where it's encapsulated or where parts of that executable is encrypted. This does not really dictate whether or not it's malicious in nature. It could be just protecting something within the executable. Like let's say a license or something like that. However, with ransomware, you'll find that the PE sections have a higher entropy, and then we can then essentially use that for detection, right? So with machine learning, specifically in security, specifically with detection of malware as well as ransomware, data sets aren't available in a raw format. Usually you find researchers doing experimentation with regard to a specific approach on how to detect information, and usually that output is then published with their results, but never that raw data. So it means that data set that has been developed is only specific for that focus. So I've also then developed a platform called Malfi, and basically that allows us to upload Cuckoo Sandbox reports, which essentially is a report that you can get generated from a sandbox environment, which tracks all of the things like the strings, the PE information, the API call analysis, the process memory allocated, and so forth. So it has a large number of data within those reports that you could then use for various methods of detection. So the way Malfi platform works is basically these Cuckoo reports get uploaded and categorized such that we can also then build data sets specific to a category. So extending from just ransomware, we can look at Trojans or anything else. And then we have a dataset generator. And because these reports are in JSON format, we allow the end user to essentially write their code to extract pieces of information from this JSON document and then build data sets. So I've used this platform to generate the PE information for my machine learning process, and it's very simple and easy to use, and that is the code essentially that was written to extract the information to build a CSV file that you just plug into machine learning. Okay. So after generation, the data set took approximately 26 minutes, spanning across 121 gigabytes of reports. So report data, with the number of samples, in this case the number of reports being 3,084, and it generated 8,599 rows, that includes the headers, and 5 columns. Okay. Now for machine learning purposes, we obviously cannot use the number column and the category. So in this case we didn't use the category and the number column just because they are predictive. We don't want that column data to influence the machine learning algorithm we're learning at any point. Okay. So looking at experimentation, so we targeted different forms of machine learning algorithms. So we looked at tree classifiers, which is simple rule-based sort of classification. Very common decision trees used in security due to its speed and its ability to detect patterns much quicker. Tree classifiers also give you a rule-based structure, like a tree structure, which security analysts can actually then go and read and actually see how the decisions-making process is actually occurring, as opposed to things like neural networks and so forth, which act like black boxes. So nobody would really know what's going on behind the inner workings of that algorithm, and that's not ever exposed to anybody. Okay. Then we also look at boosted classifiers. So boosted classifiers essentially is very similar to the tree classifiers. The only process involves is doing it over a number of iterations. So building multiple models and evaluating them and continuously improving that until the number of iterations have reached. And then we look at probabilistic classifiers to bring in some stats and some randomness between distributions of the data set. So a good algorithm that we use there is naive bayes. And then clustering classifiers, which basically groups similar data. So algorithms there are k nearest neighbors. So basically you're looking at a scatter plot and you're seeing whatever is closer to that single point. And then we also use support vector machines, which draws hyperplanes in the search space to differentiate between classes. Okay. So hyperparameter tuning. This is simply used in order to cater for various types of configurations. So more often than not, existing machine learning libraries have a bunch of parameters that you can tweak. They're often set to a default value that has been considered the best for a generic purpose. However, that is not the same for every single application in which machine learning algorithms are used in. So therefore, we use hyperparameter tuning to basically adjust the different parameters that are available through these libraries, and basically that then allows us to find what configuration of the machine learning algorithm we can use to get the best possible outcome. Okay, so you don't need to worry too much about those parameters. So that's just the parameters that was used for hyperparameter tuning. Then the results that we get is basically a classification, but from the classification we also have a bunch of other metrics that will allow us to determine whether or not this classification is good or not. So we have things like true positives, false negatives, and so forth. That's just basic normal security. And then we have other metrics like the recall, the precision, log loss, and area under the curve, the AUC, which is often very important when drawing a receiver operator curve, which we'll get to just now. But most of the times in machine learning, we always look at the accuracy. So this accuracy is a value out of 1. So if we look at the decision tree, does this have a laser pointer? Okay, no, it doesn't. If we look at the decision tree, which is in this column here, we find that the accuracy is 98.8%, and the latency involved here is 1.5 milliseconds. So this is how fast the actual model will be able to detect giving the incoming data that we saw earlier on. If those records are fed in, it will take 1.5 milliseconds to determine whether it's ransomware or not. And as we can see, random forest is about 13 milliseconds. That is because random forest builds multiple forests, so that's why that complexity comes into the play. And then with k nearest neighbors, we can see it takes 89 milliseconds. So that's because of the clustering involved. Okay. So visual representation of this. So here we have the F measure accuracy and the linear accuracy. So from all of this, we can see it's a fight between decision tree and random forest, which is the actual best. However, we can see that random forest performs ever so slightly better than decision tree. However, is the problem, right? So if you look at a decision tree, it can do it in 1.5 milliseconds, whereas a random forest does it in about 90 milliseconds. So given that it's detection and given that it's ransomware, we do not want to increase the time of detection, so therefore we go for the fastest result. So here's a receiver operator curve. So this determines how accurate a model is. And what this does is, if it's a straight line, that's a random classifier, which means it's as good as guessing. And the goal of a ROC curve is to get a right angle at the top. So that, in other words, we get the value AUC of 1. And that means the classifier 100% confident in every prediction that it has. So over here we can see that decision tree classifier is 97%, and random forest classifier is 99%. So given these results alone, the random forest would be the best or ideal classifier. However, we have to then do validation testing. And this is just done to ensure that we don't take this a classifier based on the statistics. We also benchmark the top 3 classifiers to see whether or not they are better in other circumstances. So for this purpose, we looked at decision tree, random forest, and XGBoost using validation testing. So this is a separate data set that was partitioned from the original data set, such that this data that the algorithms now see has never been trained on and has never been seen before. So benchmarking used 1,555 malicious records and 138 benign records. Now there is a bit of a imbalance between it. However, it does not really matter because we need more bad samples to determine from the good samples. Okay, and due to the benchmarking, we can see that decision tree gets a 98.29% accuracy, as well with random forest gets 98.58. Although random forest is also then slightly better in this case. However, due to the latency being lower, we use decision tree as the ideal classifier for ransomware detection. So in conclusion, the p-entropy has actually proved to be a fast and accurate way to detect ransomware. And more often than not, machine learning in security, or cybersecurity for that matter, is a growing topic. It enables us to detect malware and ransomware at a much faster rate than a human would. I mean, you can compare 1.5 milliseconds to somebody analyzing the processes in a Windows operating system. That is easily minutes or even half an hour that would take a human to do. So we can then also look at integrating p-entropy into existing detection methods, as well as using p-entropy to provide early detection of ransomware, which is essentially the goal of ransomware. We want to detect it and stop it before it even has the opportunity to encrypt a single file. So for future work, as I've mentioned, with malware specifically, data is very hard to come by, and when we talk about data, we're talking about the raw data, such data that you can actually look at multiple attributes and rather than a specific focus. Future work would then also be chaining multiple machine learning models together to improve better results. However, that is a double-edged sword because that also then comes at a cost of latency. Okay. And then also further research is what my research is heading in towards, is to provide a multi-detection framework and integrate digital forensics on top of that. And that is the end of my presentation. Thank you very much.
Thank you very much. Can we have our second speaker? Mr. Christopher Jadavari, and the talk is continuous of education on Android and mobile devices.
Christopher, isn't it funny to be on that side of the receiving end? Because usually Christopher is doing what the other guy is doing.
Now I can see. Okay. I can just put it. Good morning, ladies and gentlemen. I'm Christopher Njarawani from University of Pretoria, Computer Science Department, under the supervision of Professor Ndlopfu. He's sitting right here. Okay, so I just want to thank everyone for being here and also for listening as well. So what I'm doing is I'm doing continuous authentication on Android mobile devices. Okay, so basically the first slide I'm going to talk about the overall overview of my presentation. So what I'm going to do is I'm going to look at authentication, and then I talk about continuous authentication, and also look at the need for advanced authentication techniques, and also I'll look at typing speed, stylometry, and also my prototype. Don't worry much about the details of this at this stage. I'm going to explain everything later on. Okay, so what's the problem that I'm trying to address? So usually, I'm pretty sure that everyone in here, we are so dependent on our mobile devices. To such an extent that we do a lot of things on our mobile devices, be it sending messages, banking transactions, basically a lot of things. So what I'm trying to do is I'm trying to address the problem of unauthorized access. Maybe you just left your phone there. Someone comes in. I don't want that person who comes to actually access your mobile devices. I'm pretty sure we all know why. Emails, your text messages, maybe your spending history, your habits. Someone might even look at that information and usually that's confidential. And that might even lead to identity theft as well. So I'm trying to make sure that there isn't any unauthorized access on our mobile devices. So now, I'm pretty sure when we look at authentication, we all know the traditional way. Password, PIN. What if I know your password? What if I know your PIN? It means I can be able to access your mobile devices without you authorizing me to do that. So what I'm trying to do is now, the solution now, we have to introduce maybe some sort of like continuous authentication, which is different from the normal authentication that usually happens at the initial login. So with this continuous one, maybe we want to do it periodically. Someone might say maybe after 5 seconds, after 30 seconds, or maybe after 1 hour. That's basically what I'm trying to introduce here. So can we use password and pins periodically? Do you think we can? I don't think so. Just imagine you are using your mobile devices. Maybe you are in the middle of a conversation with someone. Then you get a message pops up to say, enter your password. Obviously, that's impractical. Therefore, we have to introduce sort of like seamless approaches which doesn't interrupt with user activities. And also these seamless approaches, they need to be secure and also user-friendly. No interruption of whatever you're doing with your devices. Okay, so the research at hand, what I'm trying to do is I'm trying to combine stylometry and the typing speed. So why? So if you take any of your mobile device, like any user of a mobile device, the most common activities that you usually do, it's either you're typing or you're scrolling. That's the most common. Therefore, that's why I'm trying to focus on stylometry. The practicality of it, obviously, that's why I'm saying you're either typing or you're scrolling. Maybe you're reading news or your favorite, maybe Facebook, Instagram. Okay, so maybe it's important that I also dive into what exactly is stylometry. So stylometry is basically the analysis of one's writing style. That's a simple, shorter definition. What does that mean? So what it means is we all have our unique way of writing. For example, some people, they like using punctuation. Others, they like using certain words. Others, they like using capital letters. So this unique way of writing can actually be quantitatively expressed. Maybe to explain a bit about that, let's say I'm given any document. Let's say maybe it was written by Prof here. I can actually prove that this is Prof because I know how he writes, maybe his average word length, his paragraphs. But when we look at mobile devices, can we actually say we have these long messages? We have short messages. Meaning to say now we need to come up with some sort of like ways that we can actually apply to these short messages. So my focus, I'm using stylometry, but I'm looking at short messages. The other thing is, let's say I get access to maybe Eunice's phone, my friend here. Maybe she just went outside. So usually the window period, I just have it for a very short period of time. The window period doesn't allow me to type a lot. So usually I'll just type a shorter message. So we need to devise methods that can actually detect those short messages. So what I'm doing is on those short messages, I'm using, never mind about the way I'm going to pronounce that word, Levenshtein distance. So what it does, it's like, it actually calculates, you get a numerical value, the number of additions that you can do given two strings. Let's say you're given 2 words or two sentences, right? So basically it calculates the number of additions or deletions that you need to do to make sure that these strings are the same. That's basically what I'm trying to do. So I'm using left and distance, and this left and distance can actually be applied at word level, at sequence level, and paragraph level. Given that I'm looking at short messages, obviously it makes sense that it's applied, it works on word level, because I'm looking at short messages. Okay, so that page I'm trying to discuss some of the various stylometric techniques. So stylometry, you can call it stylometry or you can call it stylometry techniques. So there are various techniques that I'm using in my research. For example, the bag of words, meaning to say I can always have a collection of the most common words that you like using. So every time, let's say when you type a sequence of words, I can actually compare that if I have it in one of my bags there. So there's bag of words, and also you can look at structural feature analysis. Basically, structural feature analysis looks at the structure of your text or your charts or your messages. Indentation, maybe paragraph. Are you someone who is like, maybe you type 5 words, then you put a lot of space? That's basically structural. And then you can also look at syntactic analysis as well. Use of question marks, exclamation marks, comma. And then we can also look at n-gram analysis. So n-gram, basically, it refers to, let's say if we say 2 gram, it means you are looking at words that are made up of 2 characters. 3 gram, you are looking at, for example, a word like WHO, who, that's a 3. That's what I'm doing here. So now, I'm also trying to combine my stylometry and the typing speed. The question now is, why typing speed? If you remember, I once mentioned that there are 2 common activities that one has to do if you have your mobile devices. Either you're typing or you're scrolling. So I'm looking at the typing speed. To be more specific, the typing speed of 5 character text blocks. Why 5 character? If you do a little bit of Googling or maybe a little bit of research, you find out that the average English word is 4.7 characters. Obviously, we can easily round it up to 5. That's why I'm focusing on 5 character text blocks. Okay, so what I'm doing is I'm not using machine learning as per se. What I'm using is fuzzy logic. So fuzzy logic basically deals with the degree of truthfulness. So what I'm doing is, since I told you that that left and distance, it works well with numbers. Typing speed, it's still numbers. I can calculate moving averages, weighted moving average. Let's say you are in any session at regular intervals. I can calculate weighting moving averages, and then these weighting moving averages, now I can map them to membership functions. Do they belong to these membership functions? Let's say you're given a session. I've weighted moving average 1, 2, 3, 4, all right? This one, the most recent one, I can actually compare it to these previous ones. How? I think it's simple. You can just maybe, you say, I get the highest value and the lowest value, and then you try to map it to, if it's in between there, we can say that's most probably you. And then after that, then I can make a decision. So the current state of the prototype, it's already there, but with the typing speed, it's promising, and I've gotten some results. That's promising. And then the stylometry, the one that's where I'm using that left and distance, it's partially promising, but I'm still working on it. Okay, thank you.
Thank you very much. And now for next speaker. Is het Henry Gidudu, real-time risk assessment in vehicular ad hoc networks.
Okay, good afternoon, everyone. I'm called Henry Gidudu, and I'm supervised by Professor Jan Elf. And we're trying to look at real-time risk assessment in vehicular ad hoc networks. So yeah, I do hope you enjoy the presentation and you get to learn something. I'm not going to take long. I'm going to be pretty much fast, so please hang in there. We'll be on time for lunch. So, to kind of jog up your understanding, I'll start with putting up a hypothetical explanation of risk. Every day when we wake up, we deal with some sort of risk assessment in our daily lives. When you wake up, we either decide what you want to eat, which you're driving, which path you want to take. Maybe if you're also deciding where you want to take your child to a hospital, you weigh in and then assess which decisions you want to make. So that's us in our human life. However, we don't apply, or we don't usually apply the same logic when it comes to information systems. For some long time now, the information systems have been based on a one-off method of risk assessment, whereby they leave it with production. When I say production, I mean the companies, or they bring in one security expert annually and then performs a once-off risk assessment. However, that works with the traditional IT systems. Right now, with the evolution of technology, with 5G, with AI, we have been faced with a phenomenon whereby now most of our physical activities we do in life have a certain aspect of digital technology attached to it. For example, on average, we may find half of us are putting on smartwatches. These smartwatches are connected to something. So that means we can no longer leave risk assessment only to a once-off activity where we only do it once and then leave it at that. So to do that, we're trying to come up with a framework whereby we can now extend risk assessment to a more human logic of where we do risk assessment continually, and to the extent that at any particular point T, you can actually perform risk assessment. So risk has a negative aspect. So the reason we do risk assessment is at the end of the day, we have to know when we accept to live with it, or to do something about it, which is to mitigate it. So the whole point we are now looking into risk assessment is to find how we can continuously do it and then make more guided decisions into our security mechanisms. Yeah. So, as I've already said, that now in our everyday lives, we are interfaced with some component of digital realization in our lives. The other component that has been so much now sucked up by the digital world is our cars. Every car right now has some sort of network connection. It may be either the Bluetooth, which is the most minimal network. It may be your key, the keyless opening. That's also a network of some sorts, which is an ad hoc network. So, and then it goes as far as now cars communicating to each other. For example, Francisco has a lot of robot taxis that communicate and then self-drive. So they have a sense of communication between each other. So as we picked out one of these as the emerging technologies that really requires real-time risk assessment, and we believe it's a good case study that we can use to kind of push our arguments for real-time risk assessment. So for a small background, VANETs are basically just self-organized networks. Self-organized, they connect to each other. They don't have a central controlling point. For example, for traditional networks, to be a router. So what they do, the key point, they've been in development for some time now, the past 20 years, but they're seen as the platform for self-driving cars. And we all know the self-driving car generation is upon us. Let's say in 10 years, we will be into that generation of self-driving cars. So in order to have that communication between cars, research has been ongoing to come up with the mechanisms where cars can communicate each other as driving along the road. There's been other applications that you use in your daily life, for example, Google Maps. Those applications also vehicular applications, but those require human interaction, whereby you update, I'm here. For example, some of you use Waze. In the case of South Africa, you see a police officer somewhere, and then you update on the Waze application, a police officer is here. So everyone sees it, and then you try to avoid it. But now with Vanets, they're creating a platform where cars can communicate with each other, even without human interaction. And with that, one of the technologies that has really pushed that is the IEEE 801P protocol, which is almost fully dedicated to vehicle-to-vehicle and vehicle-to-infrastructure communications. So why do we need, or why Vanets? Vanets are built or are designed in the sense that first they're going to transmit safety warning signs. Then they transmit locations. So with this information, we can actually fully at any particular time know what's going on, and then how do we help each other before, and then we can also perform guided decisions. Before you do anything else, you can plan your routes in real time. So they're really a good platform that will really further self-driving cars. So with that background, this is a small overview. Then I'll explain a little about this overview. As you can see, we have this is a vehicle-to-vehicle communication, whereby the cars are able to communicate to each other without any other network component between them. So this is one domain of the vehicular ad hoc networks where vehicles communicate to each other. And then we have the vehicle to road infrastructure, whereby they can communicate to roadside infrastructures. And then we also have another domain that hasn't been put here, where vehicles will be able to communicate with everything, which is the internet. For example, an example that I can use, if you heard of it, there's one scenario used in the Dakar rallies where they're trying to locate drivers in case of safety issues. They use the Vanet such that if a driver is lost, they can always connect to the satellite and then they can locate to them. So this is what we're dealing with. It's just the overview of the Vanets. So with that small overview, what challenges do we really face with the Vanets? This is a Venn diagram of challenges. We do have privacy challenges. We have security challenges. In security, we have the confidentiality, which is also part of a little bit about privacy. But when it comes to Vanets, the privacy issue is a little bit more pronounced or highlighted, so it needs to be tackled alone. And then we have integrity, and then we have availability, and then reliability there. And then on the other side, we have location privacy and user identity. And then in the middle, we have safety, a safety challenge. So any impact or any failure in either security or privacy has an actual physical impact on the safety of the drivers. So unlike our traditional IT systems, when you're hacked, you will incur a financial loss, you will lose your data, or maybe you may be sued for privacy infringement or something of the sort. However, with Vanets, the consequences are a little bit very dire, so we cannot wait to perform a risk assessment, or we can always not leave the detection of risks and threats in the Vanets to an aftermath when a problem happens. So that's why it really calls for the real-time risk assessment. So I've mentioned the challenges a bit. These are in real-time some examples of already some of the incidents that are happening, security incidents that are happening. One of the most recent is I like him a lot. He's not even a security expert. He's not anything. He's an artist that draws. He was able to block a street. This is in 2020. He was able to block a street for almost 3 hours by using 99 phones and a wagon. How? He put the phones in the wagon and kept on pulling them as he was moving. So he tricked the algorithm, the Google Maps algorithm, to think the whole street was packed with cars. And yet it was an empty street. So this just shows, and he's an artist, he doesn't have the knowledge to actually perform an attack, but it's as simple as doing this, and he was able to block the whole street. So this just shows you the consequences that can arise from the breach of such networks such as the VANETs. And then the other one, which was a popular one, is the Jeep Krieki. I think I pronounced it correctly. In 2016, that was able to be hacked through the Bluetooth. So the Bluetooth connection to a phone to the drive, it was able to be hacked, and then we were able to take the control of the steering system and then the infotainment system. So with all these highlighted, and then the same thing was done for the Ford and then the Toyota. So with this just shows us why we need the real-time risk assessment approach to determining these risks, because the environments of the cars keep on changing. Therefore, we can't limit the real-time risk assessment to the parameters of only one environment. So we have to be able to, as the environment changes, our risk assessment values and figures has to adapt with the changing environment. Yeah. So when we come to risk assessment itself in VANETs, as an emerging technology, nothing much not nothing much, but little has been done. So if you look around all the major journals, mostly for computer science, that's Scopus, DBLB, ACM, IEEE, you only come up with about 3, without 6 papers that have been done with risk assessment. And in the 6 papers, one still takes on the static approach to risk assessment, which is a once-off approach. With then about 5 take on a dynamic risk assessment approach. The dynamic risk assessment approach is where the risk assessment is triggered by an event. It can be performed at the time, but you wait for an event. That's an aftermath still. We can only not take on the dynamic risk assessment approach. And then only one has been done for the continuous risk assessment. And then in the papers still, most of them only look at security, and then one looks at safety, one looks at privacy and security, and only one looks at privacy. So our goal is, how do we combine security, privacy, and safety, and come up with a real-time risk assessment that can be used, adapting all the 3 in one. So that's what we're trying to do. So with that, since there's limited, we try to look at what's going on in risk assessment. We also did a study. We did some review of what is happening in risk assessment in general. We concentrated mainly on safety-specific cyber-physical domains, whereby we looked at insurance, transportation, oil and gas, and a lot has been dealt in health. We looked at these domains because they also bring in that safety complexity, whereby consequences lead to human injury or some kind of physical consequence on the population. So when we did, we categorized what we found. We looked at what they were doing. We specifically concentrated on quantitative and semi-quantitative. We also looked at dynamic, continuous, and real-time risk assessments only, because that's what we're interested in. And then we looked at methods for the past 20 years. And then our area of focus was mainly, we wanted to focus on how do they approach the real-time, their risk assessment, what methods do they use, and what tools do they use. So again, you can still see dynamic is still leading. A lot of people do a lot of dynamic risk assessment, but few people do continuous risk assessment. And then again you see, which is also the same thing here, if you can see clearly, that's dynamic and then continuous is the same thing. You can see most of the biggest part is still dynamic. However, our area of interest was the graph here. Initially, with the whole prominence of machine learning, you could think, we expected to find a lot of risk assessment approaches that have kind of employed machine learning. However, you can see machine learning only comes so much into play. In 2009, I realized this is one of the initial stages of when machine learning was becoming prominent. And this could have been one of the reasons why it's there. The only time I understood why it became prominent was 2021, and I realized this was when we had the hype of COVID-19 and a lot of people resorted to machine learning. However, what we were interested and what we liked most was the use of fuzzy logic that has been consistent for the past 20 or so years, and is still, you can see in the orange, and still being used for the past few years. So with that, we then went on and tried to see if we can actually propose a real-time risk assessment method, again using fuzzy logic. Chris talked about fuzzy logic a bit. To put it in perspective, it's a language, it's a multi-valued modeling technique. It's a mathematical technique whereby, for example, I'm a student at the University of Pretoria, and I'm also kind of an assistant lecturer at the University of Pretoria. So if you can't say either I'm a student or an employee. So in this case, you try to use fuzzy logic and use a set of rules to define to what percentage I am a student or to what percentage I am a lecturer at the University of Pretoria. So that's just a way of just to explain what fuzzy logic is. However, the motivation for using fuzzy logic was, first of all, it has been tested, it has been used by a lot of people, so therefore we don't have to prove and then motivate a lot why we have to use it, because it's really a popular technique used. Secondly, it's the dynamic nature of the vehicular ad hoc networks. What do I mean by this? When a car is moving, the parameters of the car in Kruger Park are kind of different from the parameters of that car when it's in Sandton. The congestion it will face, the network performance that will happen for that vehicular network when it's Sandton, it will be different in Kruger. So since the dynamics of that network are constantly changing, this limits the use of those other tech tools that we saw earlier. So we chose this as one of the advantages of fuzzy logic. Then the imprecise values of VANETs. It's very hard to pinpoint. First of all, it's an upcoming technology. The values are very imprecise. So that also fell in well with the use of fuzzy logic. Yeah. From that, however, with the discussion of the current state of the research is, we are on the prototyping. But what do I mean by the prototyping? We're trying to come up with kind of a software that can be used, let's say at the end, at the user's end, and you can actually dictate, or it can perform a real-time risk assessment for you, and then depending on what value comes out of that that risk assessment, you can perform a particular action in the mitigation of that risk. So with the prototyping level, we've done a couple of designs, and we found a little bit complexity with combining safety, privacy, and security, because some of the parameters were colliding. So we decided to concentrate on security and privacy. Why? Because at the end of the day, the privacy and security consequences affect the safety. So if we can solve safety and privacy, in some sort of way we'll be solving safety. And then the other thing is, we've realized, like for example, how Prof. Elof and Prof. Hain highlighted, we may have to again use another tool. For example, we're exploring the use of Bayesian networks, or we may again use a component of AI in combination with fuzzy logic, because fuzzy logic alone may not be able to give us the results we want, or may not be able to give us the solution that is really suitable to a standard that is acceptable. So for better results, and from also the previous research, you can find that for better results, it's usually a combination of two tools that would give you a better result for the risk value. So to conclude, for those maybe, if let's say you haven't understood from the start what I'm trying to look at, basically what we're trying to do with real-time risk assessment in VANETs is we're trying to develop a real-time risk assessment method that considers both security and privacy, and we're trying to illustrate that it's sufficient enough for VANETs, considering the constantly changing environment. And why do we need to do that? We need to do that because it's important. After vehicular production, the responsibility of the vehicle goes to the user. So when you buy that car, if you buy that Jeep, the responsibility of that Jeep will no longer be on, or BMW will not be on the BMW group. After you buy it, and we have VANETs, the responsibility is on you, the user, and your way you operate your car to determine how more exposed to threats you are or not. So it is really important to come up with a method that is more useful to the users also to be able to protect themselves, or to at least detect when they are in risk or not. Yeah. So thank you, and I don't know about questions since I'm the last.
Thank you very much. So let's quickly do a few questions.
Okay.
So questions for any of the free talks.
Yeah. Chris.
Okay, there's a hand there.
Thank you, presenters. Good morning, everybody.
Yeah.
So I have a question for the second presenter. Yes. So have you considered different variations in your study? For example, when a person is typing and is in an emergency, or they have different emotions, they are angry or happy or sad, or just a general emergency, or they are panicking. So they might, the typing will be different from the usual typing. Would the phone then block that person and identify them as an attacker or a malicious user? That's the question. Thank you.
Okay, thanks a lot for your question. Yeah, the points that you are raising, they are valid as well. But I think maybe I'll try to do that at the PhD level, because now I feel like the scope of it now, because you can't necessarily have all the rules. You can always do maybe up to a certain level, and then obviously that leaves a gap that you are pinpointing. So I'll consider extending or doing that at the PhD level. Thank you.
There's a question
Christopher, so do you watch Big Bang Theory? Okay. So those who watch it will know that Sheldon actually types everything correctly, on his phone. So my question is basically, what if there are 2 or 3 or 4 people like him that types perfectly, and all the punctuation and everything is always correct in a standard writing style? Would it authenticate all 4 people?
Okay, thanks, Prof. I think what's going to happen is fuzzy logic. It's all about the degree of truthfulness. Meaning to say, somehow, maybe you will be like 80% more like me, but maybe you can't be 90. So I think since it's some sort of like degree of truthness, somehow it should pick, obviously. But now I think what's going to happen now is, what's the threshold now? Because if you put maybe the threshold at 60%, chances are high that maybe 4 or 5 people will most likely type like me. But so I think with continuous experimentation, that can raise the threshold as well, maybe to a higher value.
There's a question in the back. At least we have 2 more.
Okay, thank you very much. I'm going to address the last speaker. So the first question, it wasn't very clear to me who the threat actors are for the VANET environment. So maybe you could emphasize or speak about that. And the second question was, isn't it easier to model or to try and look at trustworthiness? So instead of risk assessment, to try and look at trust assessment. Okay, thank you.
I'll begin with, I think, the second question. With trustworthiness, I feel like it leaves out a few aspects, because if you're just looking at trust, then yeah, there can be a level of trust, but there are people trying to go beyond the trust or exploit something about that trust. Because with trustworthiness, it's just how good this thing is, and then the user can now then do an assessment and then will be comfortable with that. However, when we come to VANET, since it's a network, we have on the side where we just have attackers. It doesn't matter how trustworthy it is, this will still be attacked. I don't know if I'm answering it well.
In the case of VANET, the vehicles are really the objects there.
Yeah.
So there's typically no human intervention.
Yeah.
Okay, so the vehicles transmit their data
Yeah.
and back and forth. So the real question is, how do I know my neighbor, another vehicle, is not malicious? I think this is what I'm actually looking at.
Okay, for a deeper discussion, for example, the VANETs, the way they're structured, they do have authentication mechanisms, they do have registration mechanisms, so they all have these mechanisms in the place. For example, if you get a car, these cars are registered. They have a trust authority that has to monitor all these activities at the end of the day. So that has to be there. However, we cannot put our trust in the trusted authority to do everything. For example, because we have a scenario where we have a vehicle-to-vehicle communication where you may not have a trusted authority will not be in place, and the cars have to communicate. So in that case, there are, let's say, 3 cars moving in one direction, and there's no trusted authority. Then how do you protect yourself? How do you know you're in some sort of danger? So that's why, that's what motivates us. We cannot only leave it at having some trusted person that we can have, the overseer, because we have a component whereby the overseer will not be available. And then for the attacks, it's a network, and it's prone to almost a lot of the attacks that happen in a normal network. You can have a denial of service attack. You can have bogus information injection. For example, the trolley guy, that's the basic, he didn't inject much, but he created a sense of bogus information whereby the algorithm were thinking there are cars, but there are no cars, but it can actually inject. Because VANETs exchange, you have to exchange the location, repeated beaconing. They beacon constantly a message, a current location, and then speed, time. So the problem is we can't mask the location, because then the data becomes useless. If we don't know what location, then your warning is useless, because you're giving us a warning about a place we don't know. So we have to leave the location unmasked. So if we have that, that means, for example, that's the biggest vulnerability already with VANETs, because the location has to be visible to everyone. So with all that, it's pretty much exposed to most of the network attacks that happen.
Let's take one more question, but it must be for him. Vincent?
All right, thank you. I think it's directed to the first presenter.
Yes, that's me.
Yeah, we were looking at ransomware, and I think you presented a case where you were saying you need, was it about 1,555 messages for you to get a sample for you to be able to predict the pattern of the malware. Is that correct?
No. So what happens with machine learning is you have a data set, and then you partition it. Most of the time it's usually 2, but we did it in 3. So it's training set, testing set, and validation set. So the validation set was 1,555 records.
All right, thank you. So if we are to put your tool in a real scenario, roughly how many attacks do you think it can help you raise samples of 155? Is this like 155 individuals? Sorry, 1,555 individuals, or like what are we looking at here?
Okay, so that's 1,555 rows of information. It does not translate directly into a number of samples. However, the number of samples that was over in the entire data set was 3,089, if I'm not mistaken. So from those 3,089, 8,590 something records were generated from that data set. So we're not transmitting each row to be a data sample. So there's multiple rows that originate from a sample, but with that sample's classification.
All right, so my question is, I'm trying to look at its practicality in an environment. Say, if an attack occurs, normally ransomware is an attack for maybe at most a week, 2 or 3 days, people get their money and they disappear. So I just want to see how fast is your tool going to pick out before it causes damage, because ransomware is not here to stay. They are just going to attack maybe for a week or a couple of days. So my worry is, will that time be enough for you to generate your test samples before these guys disappear?
Okay, so the main idea behind machine learning is you have this raw data beforehand to train a model. Once a model is trained, it can be used in practice. And then essentially that's where the 1.5 milliseconds latency comes in. That is, given that input record from the data that we have, if we have any information coming from a new sample that has not seen before, we just extract the P information and we send it to this AI model, in this case a decision tree model, and it will predict in 1.5 milliseconds whether it's ransomware or not. So basically the detection is near real time. It's almost instant.
Vision of Prof. Jan Ndlopfu, who, as my colleagues have also said, that he's sitting right here in front. I'll be speaking on privacy preservation in vehicular ad hoc networks, also referred to as VANETs. So, as Henry, I'm sure you can see that our focus area is very similar. So as he has already introduced and spoke about a little bit, technology is constantly evolving, right? There's been so many emergencies, evolutions, developments in the technological space, and this obviously includes the transportation and vehicular space, which brings us to our topic of today, or our research space of today, vehicular ad hoc networks as one of these technologies. So just briefly, just to elaborate or touch on VANETs, as Henry also spoke on a little bit. VANETs are simply just systems that allow vehicles to communicate with each other being other vehicles, with other infrastructure, and other entities on the road. They are an extension of intelligent transportation systems, which are systems that were designed to resolve and improve issues that surrounded safety and efficiency on roads. Their purpose is to improve the quality, primarily safety, but also to improve the quality, efficiency, and comfort of drivers, particularly while they are on the road. So on the left-hand side of the screen, you can see an overview, a bit more detailed than the previous one that you saw, an overview of the VANET network. Let me try to use this. You can see, let me try to use this one. You can see there are various participants within the network, such as vehicles or nodes. Then we've got infrastructural participants, also referred to as RSUs, or rather roadside units, RSUs for short. And then we've got our trusted authority, which sometimes can also be referred to as a central management center. So we see that there are various communication types that exist within the VANET. We've got vehicle-to-vehicle communications, or car-to-car communications, as some people, and mostly the European community, refer to them as, shortened version V2V. Then we've got vehicular to infrastructural communication, highlighted over there, also illustrated as car to infrastructure, or V2I or C2I. And then we've got I-to-I or infrastructure to infrastructure communications that happen between two infrastructural models. We also have hybrid communication types or communication groups, and the whole communication should I say cycle, is sometimes referred to as V2X, which is V to everything, because aside the V2I, the V2V, etc., there's also V to people, for people who probably have smart devices and so on and so forth. So V2X just covers the entire communication spectrum. You can also see on the diagram that there are various domains. So the domains just encapsulate the communication types that exist within the network. So we've got the mobile domain, or mobile and in-vehicle domain, which has to do with the car itself. We've got the infrastructural domain, which encapsulates the communications that go on between infrastructure. And of course, the ad hoc domain, which encapsulates the communication that exists between vehicles and infrastructure. Okay. So once again, we've just got a flow chart or a diagram of what the domains look like. As I said earlier, we've got the mobile and in-vehicle domain, which consists of mobile devices and vehicles. Mobile devices can include anything like smartphones or laptops, or in your smarter cars, the smart screens. Then we've got the vehicle itself and its different components that engage the network. The ad hoc, we've got the vehicle and the RSU, and the infrastructural domain consists of your RSUs and the trusted authority, or the central management centers. So simply speaking, how do they work within a network? So initially, vehicles are required to be registered with the trusted authority to get access into the network. Vehicles, or the nodes, and other participants are authenticated, and then they are free to communicate with each other within the network. So just a very basic overview on how they work. So as much as vehicular ad hoc networks have, provided a positive impact or positive contribution to our world, there have been issues, and there continues to be many issues with networks. Recall that vehicles act as nodes within a network, so if you might be thinking that how does a vehicle on its own find itself within a VANET? As a node, It is a participant. Currently, the world is still obviously evolving when it comes to the vehicular network space. So there's that. So we've got a few incidences that happened and that have happened in the past. Our first one was the Jeep Cherokee, where 1.4 million vehicles were recalled for a fault in the infotainment system. I think Henry briefly touched on this. So basically, security researchers named Miller and Balasek experimented on these vehicles, and they discovered that they were able to hack the vehicle through the infotainment, otherwise known as the entertainment system. And through this, they were able to manipulate the boot of the vehicle, I think the windscreen wipers, and different parts of the vehicle. We can already see that this can automatically affect a user while they're on the road. If the windscreen wipers are affected and the driver is driving on a rainy day, this is already affecting their safety. We've got the Nissan Leaf, which I believe is an electric vehicle. A researcher in Australia was able to, his name is Troy Hunt, he was able to hack his colleague's vehicle all the way in the UK from Australia. He was able to access his colleague called Scott's driving history, the distances that he had traveled, his vehicle information, which is already shows security, safety, and privacy concerns. We've got the Mitsubishi Outlander Hybrid, where again researchers were able to control the car lights, aircon, and heating with the intention of draining the battery. And lastly, the Honda situation happening in 2020, where 1.79 million vehicles were recalled due to a software fault. So as we can see, all the incidences that have occurred shows the existence of multiple security attacks. And if you're familiar with these attacks, you'll know that these are proofs of them in the system or in these incidences. Attacks such as eavesdropping, man in the middle, bogus information, manipulation of data, impersonation, and so much more. And from these attacks, we categorize the concerns, VANET concerns, into three spaces: the security issues, the privacy issues, and safety issues. However, as our topic is and focuses on privacy preservation, our focus for our research will be on the privacy issues. So, digging deeper into the privacy issues that exist in VANET, we broke down the issues into further categories, and I'll just go over them just briefly and how they relate with privacy preservation. So we have communication privacy. The privacy surrounding this, also known as message privacy, concerns the privacy that surrounds communication that exists within the network. As introduced earlier, a core feature of vehicular ad hoc networks is communication within the network. And so communication privacy just concerns privacy concerning communication, whether it's needed or not, and if it is, how it is implemented. Then we've got location privacy. Location services in vehicular networks, particularly vehicles, is very useful. I mean, without activating location services, it's pretty much pointless. And so ensuring that privacy of location, how it's managed, is what location privacy surrounds. Location privacy, in simple terms, just refers to the location of the user or the driver and its vehicle, and their vehicle. Then we've got identity privacy, which relates to the user or the driver's information. Using a system like Google Maps or Waze would require the user, especially if you want, if the driver prefers personalized a personalized experience, they would have to enter their personal details. And so the privacy surrounding this is what is encapsulated under identity privacy. Then we've got data aggregation and inference. As you can imagine, vehicular ad hoc networks require the use of large amounts of data. And obviously not everybody out there who is engaged within the network has a good intention. And so handling privacy in vehicular ad hoc networks while data is being collected, information such as traffic information, vehicle information, can affect the privacy of users, especially if there's a breach. And then lastly, we've got third-party services or service providers. The goal of this category is usually to avoid, the use of third-party service providers altogether, because the network won't have full control. However, in the case where they are required, things like access control and the protection of data should be looked into. So we come to a few of the solutions that have been proposed regarding the privacy issue in VANETs. As we are aware that when it comes to problem solving, there probably isn't a perfect solution. It's quite unrealistic to think of having a super perfect solution because we do not live in a perfect world. Some of the solutions that are proposed are the by design approach, first of all. So engaging the by design principles or approaches simply engages, for example, organizations to engage security and privacy as they design their new systems. Enhancing privacy leads us to the term privacy enhancing techniques, which simply is aimed at preserving and protecting the privacy of a user or groups of users by proposing efficient privacy-preserving solutions such as applications, algorithms, designs, systems, and services to protect involved users. Other solutions that are out there or that have been proposed include the use of authentication methods such as encryption or the use of pseudonyms, just pseudonymity in general, which can be used for location privacy or identity privacy, whereas instead of completely anonymizing data, we use pseudonyms as an identifier to replace the original data of the user. We've got mixed zones, which is more related to security and for message communication, encryption as well for security and for communications that exist within the network, and lastly, access control. Additionally to the pool of solutions, myself and Prof. Jan were secondary contributors to a paper that was published in 2021. The work was done in 2020, at the beginning of 2020, before the COVID lockdown, where we had a PhD student from Sweden, Leila Islami, with her supervisor, Prof. Simone, from Karlstad University, and simply we took the approach, or she rather, I just assisted, where instead of trying to look at solving the privacy issue from a technical perspective, we looked at it from the user's perspective, that what does the user actually want as a privacy choice. So these are the details of the paper if you're interested in looking at that. So for my work, specifically, it's still in progress. We are looking at proposing a VANET privacy framework. As I said, it's still in progress, so a few things that I'm looking at including for preliminaries is to have the design objectives where we look at security and privacy requirements for the framework, looking and considering legislation. For South Africa, that would be the POPI Act, and for the EU, the GDPR. Considering authentication, level 1 authentication, as I mentioned earlier, where the vehicle or participants would be registered with the trusted authority, so that would be the system initialization. And then level 2 authentication, where a continuous authentication would exist within the network to ensure that participants are continuously, checked to know and see that they are valid within the network, because obviously not everyone that enters the network has good intentions. I'm also using Waze as a platform to guide the framework design, because Waze is a tool that mirrors what a VANET looks like in application form.
My name is Idan Makas Mrauzi. I'm a student of computer science doing my master's under the supervision of Prof. Heinfenter. So I will take you through my research, of which the topic is model for generation of digital forensic report using AI techniques. So this is my agenda for my presentation. I will take you through the background, the problem statement, objectives, main ideas, and the conclusion. So mine won't be as other people has presented, where we're seeing cars and people moving. It's just the explanation of what is happening into generating digital forensic report using AI. So, as we all know, the past 3 decades are commonly known as decades of ICT, where the cybercrime has been on the rise, which actually led to to more activities, malicious activities that has been happening on cyberspace. And with that in mind, it opened up the potential for digital forensic to be more efficient and more needed into technology space. So the main problem for this research is that we are trying to address the issue of, what is more important is there has been a lack of standardized procedures and specifications in automating the generation of digital forensic report, which has recently resulted in difficulties, inefficiencies, inconsistencies in presenting the forensic findings. And as a result, there is no standardized process for automatically generating digital forensic report using AI techniques. And then the main objective is to suggest a solution that will guide and provide the procedures for generating digital forensic report in a networking environment. So we also want to achieve this. One of the objectives that we want to achieve is to propose the best AI technique that will work as an enabler to obtain relevant digital forensic evidence. So some of the main ideas is that these standards do not provide guidance as to the systematic generation of digital forensic report, as well as how to automate the digital forensic report intelligently. So the type of AI to be used into this study is the NLP, natural language processing. And it will be, so for digital forensic investigations, we actually guided by the ISO IEC 27037 and 27043 specifically. So the suggested solution makes it easier and more efficient for an investigator when compiling evidence as well as drafting the digital forensic report. Sorry. As a result of using AI to automate this process of generating digital forensic report from a networking environment, the investigator will probably do less of manual work when drafting a digital forensic report. So where I work in a bank, so there's more manual intervention in terms of generating this kind of reports when there's an investigation that needs to be done. So this is the high-level diagram of that provide guidance on how to generate a digital forensic investigation. So this is the normal ISO IEC 27043. So these are the processes that are involved. So but what we are trying to do with this research is that we are adding these processes, so we are replacing these processes like potential digital evidence examination and analysis, potential digital evidence interpretation and reporting by applying AI in this process that we get from the ISO 27043. So at the end of the day, we will have this process that provide guidance in terms of providing the investigator some sort of manual and for generating digital forensic report. So this is the detailed model for generating this digital forensic report by using AI. So one of the main key processes that are involved where AI is mostly used is here on extract file, analyze files, examining content, identifying suspicious content, and then generating the report. This will happen with just a click of a button. So this is where the AI is involved mostly, for the extraction, the analysis, the examination, the identifying of suspicious content, and generation of the report. All of these processes are happening in the background, and they used to happen manually when the investigator is typing or is extracting the evidence from a seized device. So in conclusion, this will save time in terms of documenting and drafting a report that are usually used into legal fraternity when you are presenting digital forensic reports.